Hello everyone. In this video, we are going to see the simulation of dual active bridge DC to DC converter. A dual active bridge DC to DC converter is an isolated DC to DC converter in which the input and the output terminals are isolated by means of transformer. So we are going to construct the converter in the MATLAB environment, and we are going to operate the converter in the closed loop mode. So open MATLAB and open Simulink. Let us create a blank model. And let us take the simulation parameters to be the simulation parameters for the dual active bridge converter are taken as given in the table. Now we are going to construct the converter. So we need 4 MOSFET switches for input bridge. Let us rotate this. And let us name the switches to be M1, M2, M3, and M4. And the switches are to be connected in the bridge fashion. The input side of the bridge is connected to a DC voltage source. Let the magnitude of the DC voltage source to be 100 volts. So the input side is connected to the DC voltage source. The pulses for the switches are to be given with the help of a pulse generator. And let the amplitude of the pulse generator be 5. And the period will be 1 divided by the switching frequency, which is taken as 30 kilohertz. So the switching frequency is taken as 30 kilohertz. And the pulse width, let us take it as 50% for MOSFET 1 and 2, and then 50% for MOSFET 3 and 4. So the gate terminals of the switches M1, MOSFET 1 and 2 are connected to the pulse generator directly. And for other two MOSFETs, we need to connect the pulse generator through a NOT gate. So we'll be connecting the pulse generator through NOT gate to other set of switches. So we will be connecting the output of the bridge, that is a input bridge, to the transformer through a coupling inductor. So let us take RLC series branch, and let us change the RLC to L alone, and we will take the coupling inductance value as given in the table, which is 0.0102 millihenry. And we will be connecting the bridge, output of the bridge, with a transformer through this coupling inductor. So let us use a linear transformer. So the linear transformer, it will have 3 windings in it. We will be using only 2 windings. So I'll take the 3 winding transformer, and we'll be using the SI units. And the normal power rating of the transformer, it is taken as a 200 VA as given in the table, and the switching the frequency of the transformer is taken as the 30 kilohertz. And the winding one parameters, we are going to take the winding one voltage to be 100, and the resistance of the winding one and the inductance of the winding one, they are taken as 0. So since we are going to consider the ideal case, and let the winding 2 voltage be taken as 60, and the resistance and inductance of the winding 2 are also taken as 0 and 0. Now the transformer is connected, the primary winding of the transformer is connected to the output of the transformer, output of the bridge through the coupling inductor. The output of the secondary terminals of the transformer, they need to be connected to the output bridge. So we need to use 4 MOSFET switches for output bridge also. So let us copy the bridges and copy the devices and the base to construct the output bridge. And we will connect the switches to form the bridge fashion. Output of the transformer is connected to the secondary, that is output bridge, and the output of the bridge should be connected to the load through a filter capacitor. So let us take RLC series branch and make this to just C, and the value of the filter capacitor is given as 660 microfarad. And let us rotate this capacitor, and we will connect the capacitor to the output of the bridge. And again, the load is nothing but the R load. We'll take the RLC series branch again and change this to R, and let us take the load resistance to be 5 ohms. Now we are going to operate this converter in the closed loop mode, where we are going to control the output voltage. So we need to measure the output voltage. So you take a voltage measurement block and connect the output of the load to the voltage measurement block. And the output of the voltage measurement block is to be given to a error detector, which is nothing but summer. So take sum, and the output should be connected with the minus sign to the summing block. The plus terminal of the sum should be connected to the reference voltage. So let us take constant block to set the reference voltage, and we will take initially 50 volt as the reference one. So output of the summing block should be connected to the controller. The controller is taken as the PI controller. So we will be using a PI controller. So choose a PID controller, and let us change this to PI, and let the P and KP and KA values are taken as given in the table. So KP value is taken as 0.0000085, and the integral value is taken as 0.05. the output of the summing block is connected to the input of the PA block. The output of the PA block is connected to a variable time delay circuit through a gain block. So let us have gain, and the gain of the block should be taken as 1 divided by 30 kilohertz. And the gain block is connected to the T0 terminal of the variable time delay circuit. Then the other terminal is connected to the pulse generator. Output of this variable time delay circuit should be connected to the gate terminals of M5 and M6. And the gate terminals of M7 and M8 are connected to variable time delay circuit through NOT. So we are going to connect NOT to the variable time delay circuit, and then the output of the NOT is connected to gate terminals of M7 and M8. Now the circuit is ready to run. Before that, we need to place a power GA block. So let us place a power GA, and we'll change the simulation type to be discrete, and we'll change the sample time to be 1 e power minus 7. And we can run the, before running the model, we can change the modulation model settings. The configuration type we can change, and the solver type we can change it to ODE23T, and we can change the stop time to be 0.4. Now we can run this model, and so we'll stop here. We need to place a display block to see the output voltage, and we can also see the waveform of output voltage by using scope. Now we can run. The output voltage is increasing towards the set value of 50. And it is found that the output voltage is maintained at the set value of 50 volt. We can see the waveform in the scope also. And now we can change the reference voltage to 60. And check whether the output voltage is following the reference voltage. So we can see that the output voltage is increasing towards the set value of 60 now. The output voltage can also be seen in the scope. So the PA controller is able to control the output voltage at the set value of a reference voltage. So in this video, we have seen the simulation, closed loop simulation of a dual bridge active DC to DC converter, wherein the PA controller is able to control the output voltage at the set value. Thank you.